Yes, we shall be looking at inexact first order differential equation when the first order is inexact. Now, when the first order is inexact, for example, we have x squared dx plus xy dy equal to 0. When this is texted, you will see that it is an inexact problem. This is an inexact problem. Although we could also rearrange it as y squared dx plus xy dy. You see that obviously, even in the first case, they are inexact. But let us test for exactness in this problem. Exactness test. First, p function of x comma y differential x plus q function of x comma y differential y is equal to 0 in the solution process. So that partial derivative of p function of x comma y respect partial derivative of x is equal to partial derivative of q function of x comma y respect partial derivative of x rather, and this is y. This is the test for exactness, is equal to exact. This is exactness test. Now that is to say we partialize y squared respect partial y. Yeah. That is this y squared. It is equal to 2y. Also, partial derivative of q function, which is xy, with respect to x here, this particular value, partialize respect to x, to test for the exactness, you see that this gives you y. So it is inexact, non-exact, inexact, first order differential equation. It's inexact. Now that it's inexact, and they are y variables, we will now use the integrating factor technique, IF. The integrating factor, as it were, is equal to exponential integral minus reciprocal m, or this time around you can also make use of p, reciprocal p, function of x comma y into partial p, partial y minus partial q, partial x, close differential y. This is the formula we are going to use. Of course, we can also use the other one where there will be no minus here, but here will be dx if the values are x variables. But because the value for partial p, partial y is 2y, and partial q, partial x is y variables, we use this formula. Take note. The minus can be outside. This is the integrating factor. And this integrating factor, once it is used, you now use it to multiply this equation, and the equation becomes exact, the initial question. Now, we proceed by coming up with this. You now say partial p, partial y minus partial q, partial x. We've gotten it from onset. That is equal to 2y minus y, and that is equal to y. Take note. Because we are subtracting this entity from the formula, which is already gotten. So at the end of the day, what we'll be having here will give us a relationship that will make it easier. So we progress by getting a particular entity which is related to this concept, and this gives us integrating factor is equal to exponential integral minus 1 over p, and the p factor is 2y here. You have 2y here. So by the time you are having the p reciprocal of the p factor, which is minus 1 over 2y, is into, again, a value of the y function when it is being subtracted. This is y multiplied by differential y. You see? multiplied by differential y, so that when this is gotten, we induce our relationship clearly to give you this function, because reciprocal of p, 1 over p function of s, negative sign, is reflected here. So when we subtract, we got this. So at the end of the day, you have exponential minus integral 1 over 2 is outside of dy, So take note of the relationship, so that when this p that was gotten ab initio from this relationship, the p itself is not differentiated. Take note. Obviously, we are to use the y square rather, please. We are to use the y square rather, please. So if this y squared is used, that is to say, here become minus 1 over y dy. What I mean is that the formula is 1 over p function of s comma y, and the value for p function is y squared. So that y squared is p, it's not differentiated. So we have to put y squared here. And y squared, y into y squared, you get y. And finally, it will now give us exponential minus natural log of y. Natural log of y. And the natural log of y will extend to give us exponential ln of reciprocal y. And exponential ln of a function is a function. So this gives you reciprocal y. Reciprocal y. Now, the reciprocal y, when it is multiplied with the initial equation, which is y squared differential x plus xy differential y equal to 0. When we multiply by 1 over y all through, which is the integrating factor, we multiply by the integrating factor, the if, all through. And if we multiply by the integrating factor, for example, the integrating factor, as you can see, is 1 over y. That will be 1 over y multiplied by y squared differential x plus 1 over y multiplied by xy dy is equal to 0. So that is to say, when this goes off and is off, you have y dx plus x dy is equal to 0. So that is to say that if we start the integration function of x comma y, we can now, if you partialize this with respect to y, you get 1. So partial p partial y is equal to partial q partial x is equal to 1. Because if you partialize p, which is y, with respect to y, you are getting 1. Partialize s with respect to x is 1. So partial p partial y equal to partial q partial s is equal to 1 is equal to exact. So it is satisfactory that it's an exact equation. So you now solve this exact equation normally, which will now be integral y dx plus k is a function of y. We pick this integrated with a function k with respect to y. So we now have y squared over 2. That is, if we are integrating with respect to y, we get it. But now this expression is with respect to a function of x. That will now give us yx, because we are integrating with respect to x, not with respect to y, plus constant function of y. So we now partialize f, function of s comma y, with respect to y, and that will be partial of yx with respect to y plus decay dy. So if we have this relationship, when we partialize respect to y, we'll now be having x plus decay dy is equal to the initial equation. And that initial equation is this equation. We can title this equation that we'll get here as equation 1. This is 1, the equation 1. Now, if that is equation 1, this particular equation which is a special equation that we have gotten, and the further integration to give us this gives us equation 2. So this equation 2 will now be partialized. When partialized, you now equate this to the first equation, but not at this point you use, at this point, only to x, the value close to dy, which is x. So s cancel x to give us decay dy is equal to 0, so that decay is equal to 0 dy. When integrated, integral decay is equal to integral 0 dy. So k is equal to constant c. This c asterisk will be added to equation 2, so that finally the answer to the inexact question will now give us xy, we are rearranging, plus k function of y, which is c. And this gives us the final answer.